Liquid state. Introduction. In a solid, the constituent particles are closely packed. Hence, they possess rigidity and have a definite volume and a definite shape. In gases, the molecules are completely free to move about. Therefore, they have neither a definite shape nor a definite volume. They fill up the vessel of any volume and also take up the shape of that vessel. However, in a liquid, the molecules are not fixed as in a solid, and at the same time, they have some freedom of motion, though they are not as free to move as in case of gases. Thus, they show a behavior in between that of gases and that of solid. Like solids, they have a definite volume, whereas unlike solid, but like gases, they do not have a definite shape. They take up the shape of the vessel in which they are put. This is expressed by saying that liquid state is intermediate between gaseous state and solid state. As explained above, the difference in the behavior of the three states of matter is mainly due to the intermolecular distances of separation. In a solid, the constituent particles are closely packed and may be treated as hard spheres. In a liquid, the molecules are separated by small distances, while in a gas, the intermolecular distances are so large that the molecules can move randomly within the vessel. The arrangement of particles of the three states of matter in the two-dimensional space may be represented as follows. These intermolecular distances suggest that the cohesive force in a solid are very strong, where in case of gases they are very weak, and in case of liquid they are in between. That is, they are fairly strong to keep them in the condensed state but not strong enough to hold them in fixed position. In fact, all the characteristic properties of liquids such as vapor pressure, surface tension, viscosity arise due to the nature of the intermolecular forces existing in the liquids. Intermolecular forces or the van der Waals forces. The forces of attraction existing among the molecules of a substance are called intermolecular forces or cohesive forces. These forces are of three different types as explained below. Dipole-dipole attraction. These forces of attraction occur among the polar molecules. The reason for the origin of these forces is quite obvious. Polar molecules have permanent dipoles. The positive pole of one molecule is thus attracted by the negative pole of the other molecule. A simple example is that of HCl, in which chlorine, being more electronegative, acquires a slight negative charge, whereas the hydrogen end becomes slightly positively charged. The dipole-dipole attractions then take place among the HCl molecule. Proof for the existence of dipole-dipole forces. If dipole-dipole forces exist among the polar molecules, they should have higher melting points and boiling points than the non-polar molecules, provided all other factors like molecular mass, molecular shape, etc. are the same. This is actually found to be so. For example, the non-polar molecules N2 and O2 have boiling point minus 196 degrees Celsius and minus 183 degrees Celsius respectively, whereas NO, which is slightly polar, has a higher boiling point, that is minus 151 degrees Celsius. Magnitude of dipole-dipole forces. As the charges at the end of the polar molecules are not as great as the charges on the ions in an ionic compound, the magnitude of dipole-dipole forces is therefore much smaller in comparison to ion-ion attractions or ion-dipole attractions. Further, whereas the forces of attraction between two ions is inversely proportional to r square, the forces of attraction between two dipoles is inversely proportional to r the power 7, where r is the distance between the ions in the former case and that between the dipoles in the later case. Consequently, under similar conditions of temperature and pressure, since the intermolecular distances are very large, the dipole-dipole forces of attraction among the gaseous molecule are very small. As the pressure is increased or the temperature is decreased, the distance among the molecule decreases, that is, the molecules comes closer. As a result, the intermolecular forces of attraction increases and the gas changes into a liquid or solid. The magnitude of dipole-dipole forces in different polar molecules can be predicted on the basis of the polarity of the molecules, which in turn depends upon the electronegativities of the atoms present in the molecules and the geometry of the molecules. The polarities of the molecules are usually expressed in the terms of dipole moments of the molecule. For example, comparing the molecules of ammonia and water, the dipole moment are 1.49 diopter and 1.85 diopter respectively. Thus, though both have nearly same molecular mass, the intermolecular forces of attraction are stronger in case of water than those in ammonia. Consequently, water has higher melting point and boiling point than those of ammonia. In fact, it is well known that whereas water is liquid, ammonia is gas. Hydrogen bonding. It is a special case of dipole-dipole attractions. It occurs in molecules containing a hydrogen atom linked by a covalent bond to a highly electronegative atom but small in size. Because of the large electronegativity difference between the hydrogen atom and the highly electronegative atom, the hydrogen atom acquires a significant delta positive charge and the electronegative atom acquires a significant delta negative charge. The positive hydrogen end of one molecule then attracts the negative electronegative atom of the other molecule. For example, the cases of hydrogen fluoride, water and ammonia may be represented as given below. Because of the greater polarity of these molecules, the intermolecular forces of attraction are stronger than the ordinary dipole-dipole attractions. That is why this type of intermolecular attraction is considered as a bond rather than mere dipole-dipole attraction. This type of bond is called hydrogen bond and is represented by dotted line as shown in the examples given below. To sum up, hydrogen bond may be defined as the attraction of hydrogen atom of one molecule by the electronegative atom of the other molecule in case of compounds containing hydrogen atom linked to highly electronegative atom small in size. Further, as shown above, in each case, the hydrogen atom is linked to two electronegative atoms simultaneously, one by covalent bond and the other by hydrogen bond. Thus, hydrogen acts as a bridge between the two electronegative atoms. This is sometimes referred as hydrogen bridge. Strength of hydrogen bond. As mentioned above, hydrogen bond is stronger than ordinary dipole-dipole attraction. However, it is much weaker than the covalent bond. The energy of hydrogen bond lies between 20 to 40 kJ per mole, whereas that of covalent bond is usually between 160 to 600 kJ per mole. Depending upon the electronegative atom, the strength of hydrogen bond follows the order hydrogen fluoride, water and ammonia. Dipole-induced dipole attractions. The positive end of a polar molecule may attract the electron cloud of a non-polar molecule lying close to it, thereby polarizing it. Thus, the non-polar molecules becomes an induced dipole just as it happens in case an iron piece is brought closer to a magnet. As a result, attraction takes place between the polar molecule and the non-polar molecule. Third is induced dipole attractions. It is easy to conceive ion-ion attractions, ion dipole attractions and dipole-dipole attractions. However, the next very significant question is what intermolecular forces attract non-polar molecules to each other in the liquid and the solid state. The origin of these forces was proposed by Fritz London in 1930. Hence, they are termed as London forces. These forces are thought to arise from the motion of the electron. It is believed that at any instant of time, the electron cloud of the molecules may be distorted so that a momentary dipole is produced in which one part of the molecule is slightly more negative than the rest. The momentary dipoles induce dipoles in the neighboring molecules. These are then attracted to each other exactly in the same way as the permanent dipoles. The forces of attraction between the induced momentary dipoles are called London dispersion forces. It may be pointed out that since all molecule contains electron, London forces also exist in the polar molecules. However, in the case of non-polar molecular substances, London forces are the only intermolecular forces that exist. Magnitude of the London forces. London forces are the weakest intermolecular forces. Their magnitude completely depend upon the following two factors. Complexity of the molecules. Larger or more complex are the molecules, greater is the magnitude of London forces. This is obviously due to the fact that the large electron clouds are easily distorted or polarized. Since the larger molecular size amounts to large molecular mass, it is often suggested that the magnitude of London force increases with the increasing molecular masses. Geometry of the molecules. The shape of the molecules have a significant effect on the magnitude of London forces. For example, N-pentane and neopentane have the same molecular formula, C5H12. Yet the boiling point of N-pentane is about 27 degrees Celsius higher than that of neopentane. The difference can be attributed to the different shapes of the two molecules. The N-pentane being a zigzag chain, whereas neopentane is nearly spherical. The overall attraction between the molecules is greater in case of N-pentane because these are more sites of attraction. The molecules are able to come in contact with the entire length of the molecules. Quite often, London forces are referred to as van der Waals forces. However, it is incorrect to call London forces alone as the van der Waals forces. In fact, van der Waals forces is general term which implies all type of intermolecular forces. It is interesting to mention here that based on the nature of intermolecular forces, the liquid are classified into the following type. First, ionic liquid such as molten salts. Second, metallic liquid consisting of ions and mobile electrons. Third, liquid such as water in which molecules are held together mainly by hydrogen bonds. Fourth, molecular liquid in which the molecules are held together by van der Waals forces which include interaction between permanent dipole and an induced dipole, induced dipole. Next is mathematical treatment of intermolecular forces. Let us consider the interactions between a pair of molecules. When the molecules come close together, there are forces of attraction and the forces of repulsions between them. Experimental and theoretical studies both show that the attractive forces between a pair of molecules vary inversely as the seventh power of the intermolecular forces distance between them. Negative sign has been used because force is a vector quantity, and if we take the center of one molecule as the origin with r equal to 0, the force of attraction is in a direction opposite to the vector form r equal to 0 to the second molecule. These forces are of considerable magnitude when the intermolecular distances are of the order of little more than molecular diameter. At very short distances of approach, repulsive forces become applicable between the molecules, but these are generally of small order in solids because the intermolecular distances are somewhat greater. It is found that the repulsive forces vary inversely as 30th power of the intermolecular distances, that is Fr is equal to Kr 1 by r the power 13. The net intermolecular force between the pair of molecules is the sum of the attractive and repulsive forces, that is F is equal to Fa plus Fr. Instead of forces, it is generally more convenient to study their corresponding intermolecular potential energies. Potential energy is the amount of work done in bringing one molecule from infinity to distance r from the other molecule. A plot of potential energy due to attractive forces, repulsive forces, and the net forces versus intermolecular forces is given below, where V equation is generally written in the form V is equal to 4 phi r naught by r the power 12 minus r naught by r the power 6, जहाँ पर E is the depth of the well, R naught is the intermolecular distance between distance when V equal to 0. The potential is as given by the above equation is called Lennard-Jones potential after the name of English physicists who made these studies. Next is structure of liquids. To study the structure of liquid means to find out how constituent particles are arranged within the liquid. The following different studies help in to know about the structure of liquid. Volume changes on fusion and vaporization. When a pure solid melts, the increase in volume is only about 1%, which is much smaller than increase in volume which take place when the liquid changes into vapor at the boiling point. Knowing that in a solid, the constituent particles are arranged in perfect order, the small increase in volume on melting shows that some disorder has been introduced, but large change in volume from liquid to vapor state reveals that disorder from liquid to gaseous state is very large. Hence, we conclude that the constituent particles of a liquid are not as ordered as that in a solid. At the same time, they are not as disordered as that in a gas. Second, enthalpies of fusion and vaporization. The amount of heat required to melt 1 mole of a pure solid at melting point is found to be much smaller than the amount of heat required to convert 1 molecule of liquid obtained into vapor at the boiling point. For example, molar enthalpy of fusion for ice is 6.1 kJ per mole, whereas enthalpy of vaporization for water is 40.7 kJ per mole. Greater the amount of heat absorbed, greater is the disorder introduced. Thus, when the solid melts, some disorder is introduced in the liquid obtained, but this disorder is much smaller than the disorder introduced when we change the same amount of liquid to the vapor at the boiling point. This again shows that the constituent particles of a liquid are not as ordered as that in a solid, but at the same time they are not as disordered as that in a gas. Third, X-ray diffraction studies. X-ray diffraction studies of crystalline solids show that the constituent particles within the solid crystals are arranged in a perfect order, and this order extends up to the edges of the crystal. This is called long-range order. Electron diffraction studies of gases show that the gaseous molecules have no order at all. That is, there is totally a chaotic distribution of molecules. The structure of liquid is also studied with the help of X-ray or neutron diffraction methods so that they can enter into the interior of the liquid rather than being reflected only from the surface. If, like gases, the molecules in a liquid had absolutely no ordered arrangement, there would have been continuous scattering of X-rays without maxima or minima. However, this is not the same. For example, the X-ray diffraction pattern of liquid mercury is shown in figure 2.7a. This diffraction pattern shows that there are 1 or 2 diffraction maxima at small angles, but as we move outwards from some centrally chosen atom, the maxima are damped out. This shows that in a liquid, short-range order still exists, but there is no long-range order. It is convenient to study the location of particles in a liquid in terms of radial distribution function, which gives the probability of finding a particle in the range dr at a distance r from another. These are easily calculated from X-ray diffraction pattern. In these cases, only the distance of the neighboring molecules and not the angles from the centrally chosen one are studied. The radial distribution curve calculated from the scattering curve is shown. Theories or models of liquid state. Gases and solids are two extreme states of matter. In the former, There is a total chaos of molecule, while in the latter there is a perfect order arrangement of these particles which keep on vibrating about their mean position. In both cases, the mathematical treatment becomes easy and well advanced theories have been put forward to calculate their properties, that is energy, heat capacity, entropy, etc. However, in case of liquids, the situation is not well defined. Example, cohesive forces are sufficiently strong so that they can exist in the condensed state but not strong enough to hold the particles in the fixed positions in so that they do not have some translational energy. Hence, their theories are difficult to handle mathematically. Two common theories about liquids are briefly discussed below. First is vacancy or Hall theory. This theory was put forward by Ehring and Ree in 1933. This theory is based on the fact that liquids are generally less dense than the corresponding solids. This implies that the intermolecular space in a liquid is more than that in a solid. Ehring and Ree put forward the important view that in a liquid, the intermolecular space was not random but comprised of holes and or vacancies of the size of molecular diameter. Thus, a molecule can be considered to consist of liquid molecules and the holes randomly distributed between them. Due to the presence of hole, the neighboring molecules can easily jump into them and thus show gas-like behavior. Those molecules which do not have a hole in the neighborhood cannot jump and hence show solid-like behavior. Using appropriate mathematical treatment, the mole fractions of the gas-like and solid-like molecules can be calculated. From these values, the thermodynamic properties of the liquid can be calculated. The results thus obtained for argon by Ehring and Ree were found to be in close agreement with the experimental values. Second is free volume theory. According to this theory, it is believed that a molecule in a liquid is surrounded by 10 to 12 neighboring molecules, only a small distance away from the molecule. These surrounding molecules thus form a cage or cell around the central molecule. Thus, the central molecule has to move only though a small distance to collide with any of its neighboring molecule, unlike in a gas where the molecules have to travel a long distance before colliding with another molecule. Thus, the center of the cage molecules can move within the space shown by the shaded area. The volume thus available to the molecule within which its center can move is called the free volume. Assuming the potential field within the cage or cell as spherically symmetrical, free volume can be calculated and this can be related to various thermodynamic properties of the liquid. Structural differences between solids, liquids and gases. The main points of difference between a solid, a liquid and a gas are summed up in the table below. So solid. First point, their X-ray diffraction patterns have well-defined maxima. Liquid, their X-ray diffraction pattern have only one or two well-defined maxima which damp out with distance. Gas, their electron diffraction pattern do not have any maxima. Second, solid, the constituent particles are arranged in a perfect order, that is there is a short range as well as long range order. Liquid, there exists a short range order but there is no long range order. Gas, there is neither short range nor long range order, rather there is a chaos of molecule. Third, for solid, the constituent particles are very closely packed, hence they have strong intermolecular forces of attraction and hence possesses rigidity and a definite volume. Liquid, the molecules are separated by small distances, though the forces of attraction are weaker than the solid but are sufficient enough to hold them together. Hence, they possess fluidity and have a definite volume but no definite shape. Gas, the molecules are separated by large distance, hence the intermolecular forces of attraction are weak. As a result, they have neither definite shape nor definite volume. Fourth, solid. The constituent particles have no translational or rotational motion, however, they have vibrational motion. Liquid, Their molecule have some translational, rotational and vibrational motion. Gas. Their molecules have large translational, rotational and vibrational motion. Fifth, solid. Solids have high density. Liquid. Densities of liquid is lower than that of solid but higher than that of gases. Gases have low density. Physical properties of liquid, a general introduction. We have already studied about gases in chapter 1. Liquid differs from gases in one important aspect, that is in the state of aggregation of their molecules. In the liquid, the intermolecular distances are not as large as in case of gases. As a result, the intermolecular forces of attraction in case of liquids are much larger as compared to those in case of gases. Consequently, although like gases, the liquid have no definite shape, but unlike gases, they have a definite volume. Because of the difference between the gases and the liquids as noted above, the liquids do not obey any general laws as in done by the gases. However, the liquid possesses certain physical properties which are the characteristics of each liquid. These properties help us to decide the chemical constitution of each liquid. Some of the common physical properties of the liquid are vapor pressure, surface tension, viscosity, refractive index, optical activity, and dipole moment. Now we shall take up the discussion of first four properties one by one. Vapor pressure. Suppose some liquid is placed in an evacuated vessel connected to a manometer. According to kinetic theory of liquid, the molecules of the liquid are constantly moving in different directions with different speeds. Thus, as these molecules are moving with different speeds, they possess different kinetic energy. At any particular temperature, the energy of some of the molecules may be so high that they may leave the liquid and come in the space above the liquid. This process is called evaporation. As the time passes, more and more molecules of the liquid leave the liquid and come in the space above the liquid. The molecules thus present above the liquid are called vapor. The molecules in the vapor phase are also constantly moving, and some of them strike the surface of the liquid and may be recaptured by the liquid. This process is called condensation. If the liquid is added into the evacuated vessel, then initially, as there are no molecules of the vapor, the rate of condensation is zero. However, if the temperature is kept constant, the evaporation continues at constant rate. Now, with the passage of time, as the number of molecules in the vapor phase becomes more and more, the rate of condensation also increases. Ultimately, a stage is reached when rate of condensation becomes equal to the rate of evaporation. That is, as many molecules re-enter into the liquid as leave the liquid in the same time. This state is called the state of equilibrium. The pressure exerted by the vapor at this stage is called vapor pressure, or sometimes called saturated vapor pressure, as the vapor phase is saturated with vapor at this stage. Hence, vapor pressure of a liquid at any temperature may be defined as the pressure exerted by the vapor present above the liquid in equilibrium with the liquid at that temperature. Some important results. Some important results related with the process of evaporation are given below. Cooling caused by the evaporation. When a liquid evaporates, the more energetic molecules leave the liquid. As a result, the average kinetic energy of the remaining liquid decreases and hence the temperature falls. Second, factors affecting vapor pressure. Two important factors on which the vapor pressure of a liquid depends are nature of the liquid. If the intermolecular forces of attraction in the liquid are weak, the molecules can easily leave the liquid and come into the vapor phase, and hence the vapor pressure is higher. For example, the vapor pressure of ether, acetone, benzene, etc. is higher than that of water at the same temperature. Second is effect of temperature. As the temperature of liquid is increased, the number of molecules with higher kinetic energy increases. Hence, the vapor pressure of the liquid increases. The effect of temperature on vapor pressure can be studied quantitatively with the help of Clesius-Clapeyron equation, which is log of P2 by P1 is equal to latent heat of vaporization of liquid by 2.303 AR into T2 minus T1 by T1 into T2. Thus, knowing delta HV, that is latent heat of vaporization of the liquid, and vapor pressure P1 at temperature T1, the vapor pressure P2 at temperature T2 can be calculated. Third is boiling point. As stated above, the vapor pressure of a liquid increases as the temperature increased. The temperature at which the vapor pressure of the liquid becomes equal to the external pressure is called the boiling point of the liquid. When the external pressure is normal atmospheric pressure, the boiling point is called the normal boiling point. For example, normal boiling point of water is 100 degrees Celsius. The normal boiling point for any liquid is obtained from the vapor pressure temperature curves, as shown for acetic acid in figure 2.12. Obviously, if the external pressure is higher, more heat will be required to make the vapor pressure equal to the external pressure, and hence higher will be the boiling point. Similarly, if the external pressure is decreased, the boiling point is lowered. This is the reason that a liquid boils at a lower temperature on the top of mountain than the seashore. Fourth is heat of vaporization. When the liquid starts boiling, if extra heat is supplied to the liquid, it is used up not in increasing the temperature of the liquid, but to overcome the intermolecular forces of attraction existing in the liquid and thus changing the liquid into vapor. Hence, the temperature remains constant till whole of the liquid changes into vapor. The amount of heat required to change 1 mole of liquid into its vapor at the boiling point is called the heat of vaporization of the liquid. Obviously, greater the intermolecular forces of attraction present in a liquid, greater is the heat of vaporization. For example, the heat of vaporization of water is more than that of ether, acetone, benzene, etc. Fifth, relationship between boiling point and critical temperature. Goldsberg rule. Goldsberg pointed out the following general relationship between the normal boiling point and the critical temperature of the liquid. That is, the normal boiling point of the liquid are nearly two-thirds of their critical temperature when both are expressed on the absolute scale. Sixth, relationship between boiling point and the heat of vaporization. Torsion's rule. Torsion observed the following generalization about liquids which are not non-associated and which do not have too high boiling points. Delta HV by TB is equal to 21, where delta HV is in calories and TB is in degree absolute. This is known as Torsion rule and may be stated as follows. For liquids which are non-associated and do not have too high boiling points, the ratio of heat of vaporization to the boiling point is approximately 21. These next is measurements of vapor pressure. The various methods used for the measurement of vapor pressure are generally classified into two categories: static method and dynamic method. These methods have been so named because in the static methods, the liquid is allowed to establish its vapor pressure without being disturbed, while in dynamic method, the liquid is disturbed either by boiling it or by passing a stream of inert gas through it. Some commonly employed static and dynamic methods are briefly discussed below. First is static method. Barometric method. In this method, two barometric tubes are used. These are filled with mercury and then inverted into the same trough of mercury. One tube is used for comparison with the other. In one of the tubes, the experimental liquid is introduced, a few drops at a time. It evaporates in the space above mercury. More and more of liquid is introduced till no more liquid evaporate and remains as much. The difference of levels of mercury in the two tubes is then the vapor pressure of the liquid at the room temperature. For finding the vapor pressure at any other temperature, the barometric tubes are surrounded by a heating jacket as shown in figure 2.13. Next is isotenoscope method. This method was devised by Smith and Menzies. It is a convenient and accurate method which can be used to measure the vapor pressure over a range of temperatures. The apparatus is given in figure 2.14. The main part of the apparatus is the isotenoscope, which comprises of bulb B and U-shaped portion of the tube C. The bulb B is nearly half filled with the liquid under investigation, and the same liquid is placed in the U-shaped portion which with its level about 2-3 cm below that in the bulb. The isotenoscope is placed in the thermostat A, whose temperature can be noted from the thermometer T. The isotenoscope is then connected to the rest of the apparatus, which comprises of a barometric tube D and a big bottle E as shown in the figure 2.14. The bottle E can be connected to the atmosphere or to the vacuum pump as desired so as to regulate the pressure inside the apparatus. The method involves the following step. First is the bottle E is connected to the vacuum pump and the apparatus is evacuated till the liquid boils vigorously in the bulb B. This expels all air from the isotenoscope BC. The level of the liquid in the limb L2 stands higher than in the limb L1. Second is the temperature of the thermostat is now adjusted to the desired value and air is admitted slowly into the apparatus till the level of the liquid in both the limbs L1 and L2 are equal. Under these conditions, the pressure in both the limbs L1 and L2 are equal. Under these conditions, the pressure in both the limbs L1 and L2 will be equal. Pressure in the limb L1 is the vapor pressure, whereas pressure in the limb L2 is equal to the pressure in the rest of the apparatus and is equal to the atmospheric pressure minus the height of the mercury column in the tube D. Hence, this difference is the vapor pressure of the liquid at the temperature of the thermostat. By fixing the temperature of the thermostat at any desired value, the vapor pressure can be measured at that temperature by repeating the process as described above. Second is dynamic method. The simplest dynamic method is based upon the principle that the liquid boils at the temperature at which the vapor pressure becomes equal to the external pressure over the liquid. Thus, by fixing the external pressure over the liquid at different values, the boiling point of the liquid is determined at each external pressure. Suppose the boiling points are T1, T2, T3, etc. at the external pressure P1, P2, P3, etc. Then obviously the pressures P1, P2, P3, etc. will be the vapor pressures at the temperature T1, T2, T3, etc. respectively. By plotting the pressures against the corresponding temperature for any particular liquid, a curve of type shown in figure 2.12 is obtained. From this curve, the vapor pressure at any temperature can be found. Thus, the dynamic method differs from the isotenoscope method in the aspect that whereas in the isotenoscope method, the temperature is fixed first and then the vapor pressure is measured. In the dynamic method, the external pressure is fixed first and then the liquid is heated to find the temperature at which it boils. Third is gas saturation method. The basic principle of this method is briefly described below. A known weight of the experimental liquid is taken in a closed vessel. A known volume of the dry air at a known pressure and temperature is then passed through it. As a result, the molecules of the liquid are carried with the air and a loss of weight of the liquid occurs. Air is continuously passed till there is no further loss in the weight of the liquid, keeping the pressure P constant throughout. The air gets saturated with the vapor. In the air saturated with the vapor, if N1 and N2 are the number of moles of the vapor and air respectively, Then the partial pressure of the vapor, which is equal to the vapor pressure of the liquid at the experimental temperature, will be given by P is equal to N1 by N1 plus N2 into P. If W is the loss in weight of the liquid and M is the molecular mass, then N1 is equal to W by M. Further, if air is supposed to be an ideal gas, then N2 is equal to PV by RT. On substituting the values of N1 and N2 in equation first, the vapor pressure of liquid can be easily calculated at the desired temperature. Next is surface tension. Surface tension is a characteristic property of liquid which arises due to the fact that the molecules of liquid at the surface are in different situations than those in the interior of the liquid. For example, a molecule lying inside the liquid is surrounded by other molecules and so is attracted equally in all directions. Hence, the net force of the attraction acting on the molecule is zero. However, a molecule lying at the surface is attracted more by the molecule lying in the bulk of the liquid than by the molecule lying above in it, the vapor phase. Thus, a molecule lying at the surface experiences a net inward attraction. As a result of this inward pull on all molecules lying at the surface behaves as if it were under tension. Hence, this property of liquid is called surface tension. The surface tension of a liquid is defined as the force acting at right angle to the surface along 1 centimeter length of the surface. Thus, the units of surface tensions are Dan per centimeter. Further, as a result of the inward pull on the molecules at the surface of the liquid tends to contract to the smallest possible area for a given volume of the liquid. It is for the reason that the drops of a liquid are spherical because of a given volume, a sphere has minimum surface area. To increase the area of surface, some work has to be done against the inward pull. For example, consider a soap solution film contained in a rectangular wire frame ABCD in which the side CD is movable. In order to extend the surface area of the film, the movable wires has to be pulled from position CD to position EF. Thus, some work has to be done against the force of surface tension. The work in ARGS required to be done to increase or extend the surface area by 1 square centimeter is called surface energy. The unit of surface energy are therefore ARGS per square centimeter or joule per square centimeter. Surface energy is equal to work per square centimeter. These units are the same as those of surface tension. Thus, the surface energy is same thing as surface tension. Hence, the definition of surface energy is sometimes taken as the definition of surface tension. The values of surface tension of some commonly liquids at 20 degrees Celsius in 10 centimeters are given below. Like of water 72.8, nitrobenzene 41.8, benzene 28.9, acetic acid 27.6, chloroform 27.1, acetone 23.7, ethyl alcohol 22.3 and so on. Some important results. Spherical shape of drops. As already explained, surface tension tries to decrease the surface area of liquid to the minimum. The drops of the liquid are spherical because of given volume. A sphere has minimum surface area. Second, rise of a liquid in a capillary tube. Suppose one end of capillary tube is put into the liquid that wets glass. It is found that the liquid rises into the capillary tube to a certain height. This rise is obviously due to the inward pull of surface tension acting on the surface which pushes the liquid into the capillary tube. As discussed, it is because of some reason that oil rises into the wick of an oil lamp or water below the surface of the earth rises to the plants through the roots or ink rises in a blotting paper. It may be mentioned here that in case of liquid which do not wet glass, that is mercury, the level inside the capillary falls below the level outside. Further, whereas the upper surface of a liquid that wets glass is concave, that of mercury is convex. Such a surface is therefore called meniscus. The angle which the curved surface makes with the wall of the tube is called contact angle and is found by drawing a tangent at that point. Third is interfacial tension. If two immiscible or partially miscible liquids are taken in a vessel, then the surface tension acting along their surface of separation, that is along this interface, is called the interfacial tension. Its value is generally intermediate between the surface tension of the two liquids, but sometimes it is less than both. This is due to the fact that at the interface, the molecules of one liquid are attracted by the molecules of the other. In fact, the surface tension of a liquid is also an interfacial tension, the two phases involved being the liquid and the vapor above it. Fourth is surface active agent. There are certain substances like soaps, certain sulfonic acids, and certain other organic compounds like methyl alcohol, ethyl alcohol, acetone, etc., which, when added to the water even in small amount, decrease the surface tension of water to a considerable extent. Such substances which lower the surface tension of water are called surface active agents. It is for this reason that the soap acts as a detergent. For example, if grease is sticking on the surface of a cloth, water does not wet the grease and hence is not removed by water alone. However, if soap is added to the water, it lowers the interfacial tension between water and grease. As a result, the grease mixes into the water and hence is removed from the surface on the cloth. Effect of temperature on surface tension. The surface tension of liquids generally decreases with the increase of temperature and becomes zero at the critical temperature. The decrease in the surface tension with the increase of temperature is obviously due to the fact that with the increase of temperature, the kinetic energy of the molecules increases and therefore the intermolecular attraction decreases. An important relationship between temperature and surface tension as detected by Otvos is as follows. Gamma into m by d raised to power 2 by 3 is equal to k Tc minus T, where m is molecular mass of liquid, d density of liquid at temperature T degrees Celsius, Tc is the critical temperature of the liquid, gamma is the surface tension of the liquid at temperature T degrees Celsius, K is a constant. Next is sixth is effect of adding increasing amount of soluble substances, that is impurities, on the surface tension of water. It is observed that the presence of other soluble substances affect the surface tension of the liquid considerably. The impurities which tend to concentrate on the surface of the liquid compared to its bulk lower the surface tension. For this reason, substances like soaps, detergent decrease the surface tension sharply up to cmc and then remains almost unchanged, whereas substances like methyl hydroxide, methanol, ethanol, etc., lower the surface tension slightly. Inorganic impurities are present in the bulk of the liquid and tend to increase the surface tension of water. The result of different types of impurities on the surface tension are shown in figure 2.20. Next is the measurement of surface tension. There are many methods which can be used for the determination of surface tension. Out of these, the three convenient and most commonly used methods are briefly discussed below. First is the capillary rise method. This is the most accurate method for the measurement of surface tension. The principle of this method is as follows. Suppose one end of the capillary tube is put into a liquid which wets glass. Then the force of surface tension pushes the liquid into the capillary to a certain height. till the force of surface tension acting upward balances the weight of the liquid column acting downwards. Suppose height of to which liquid rises in the capillary is equal to h centimeter, density of the liquid is equal to d gram per centimeter cube, inner radius of the capillary is equal to r centimeter, surface tension of the liquid is gamma dynes per centimeter, and contact angle is equal to theta. Then component of surface tension acting in the vertical direction is equal to gamma cos theta. Inner circumference of the capillary is equal to 2 pi r. Force of surface tension acting upward all along the circumference is equal to 2 pi r gamma cos theta. Weight of the liquid acting downwards is equal to pi r square h dg, where g is acceleration due to gravity and pi r square h is the volume of the liquid column. Hence at equilibrium 2 pi r gamma cos theta is equal to pi r square h dg. For most of the liquid which wet glasses, theta is equal to 0, so that cos theta is equal to 1. So gamma is equal to r h dg by 2. Thus the only two parameters that need to be measured are the inner radius of the capillary tube and the height to which the liquid rises. The former is measured with the help of a travelling microscope, whereas the latter is measured with the help of cathiometer. The uniformity of the bore of the capillary tube is tested by placing a thread of mercury 2 to 3 cm in length inside the tube and measuring its length at different points along the tube. Moreover, by taking the weight of the mercury and knowing its density at the room temperature, the volume of mercury can be calculated. Knowing the length of mercury thread, the radius of capillary can be calculated. Second is the stalmanometer method. This method is carried out in two different ways as follow. Drop weight method. This method is based upon the principle that the weight of a drop falling slowly out of the capillary held vertically is directly proportional to its surface tension. Thus, for two liquid, the drop of which fall almost at the same rate out of the same capillary. So, gamma 1 by gamma 2 is equal to m1 by m2, where gamma 1 and m1 are respectively the surface tension and weight of each drop of the first liquid, and gamma 2 and m2 are the corresponding values for the second liquid. Thus, knowing the surface tension of one of the liquid, that of the other can be determined. The apparatus used is called stalegometer and is shown in figure 2.22. It resembles a pipette with the bulb in the middle and a markham on the tube above the bulb. However, the lower portion is made up of a capillary with the flattened tip. The procedure consists of the following step. The stalegometer is first cleaned with the chromic acid to remove any greasy matter sticking on it and then thoroughly washed with water. It is clamped vertically in a clamp stand and a rubber tube with a pinch cork is attached to the upper portion. Distilled water is sucked into the apparatus and then the pressure adjusted with the help of a pinch cork so that the rate of fall of drop is about 15 to 20 drops per minute. 10 drops of water are allowed to fall into a clean weighing bottle which has already been weighed when empty. The weight of the weighing bottle along with the drops is taken. The apparatus is now rinsed with acetone and thus allowed to dry. Now the experimental liquid is sucked into the stalegometer. The rate of fall of drops adjusted as before and 10 drops of the liquid taken into the empty weighing bottle and the bottle weighed. The calculations are then carried out as follows. Suppose weight of the empty bottle is equal to W1 gram. Weight of the bottle plus 10 drops of water is equal to W2 gram. Weight of the bottle plus 10 drops of water liquid is equal to W3 gram. Weight of 10 drops of water is equal to W2 minus W1 gram. Weight of 10 drops of liquid is equal to W3 minus W1 gram. If gamma W is the surface tension of water and the surface tension of the experimental liquid gamma 1 will be given by gamma 1 is equal to W3 minus W1 by me W2 minus W1 into surface tension of water. Next is drop number method. As it is more convenient to count the number of drops formed from a certain volume of liquid than to make the weight of a drop of a liquid, therefore the above mentioned method may be carried out in an alternative manner as follows. Suppose the number of drops formed from V ml of a liquid is equal to N. Then weight of one drop of the liquid is equal to V into D by N, where D is the density of the liquid. Thus, if form the same volume of the two liquid, the number of drops formed are N1, N2 and D1, D2 are their respective densities. Hence, knowing the number of drops formed from the same volume of two liquid, knowing their densities and knowing the surface tension of one of them, that of the other can be calculated. In the procedure, the apparatus is cleaned and clamped vertically as before. Distilled water is first sucked into the apparatus up to the mark M. The number of drops falling out of capillary is noted. The apparatus is rinsed with acetone and dried. The experimental liquid is now sucked in up to the mark M and the number of drops formed is counted. The result is then calculated using the formula derived above. Third is the tensiometer or the torsion balance method. It is a commercial method used for the rapid measurement of surface tension of a liquid. The method was first devised by Wilhelmy and later developed by Dunois. The method is based upon the principle that the force required to take out a horizontal platinum ring dipping just below the surface of a liquid is directly proportional to the surface tension of the liquid. The platinum ring used is usually of about 4 cm diameter and the liquid is usually taken in a watch glass. The force required is measured either by attaching the platinum ring to one end of the beam of a sensitive balance and placing weights on the other side or by using a special balance called torsion balance. In this balance, the platinum ring is attached to one end of the beam and the other end of the beam is fixed to a stretch wire which can be given a torsion by a suitable device. The amount of torsion just sufficient to take out the ring can be recorded on a circular scale attached to one end of the wire. The experiment is first performed with water and then with the experimental liquid. Suppose the torsion angles are theta 1 and theta 2 and their surface tensions are gamma 1 and gamma 2. Then gamma 1 by gamma 2 is equal to theta 1 by theta 2. And thus knowing the surface tension of water, then the experimental liquid can be found. It may be noted that out of the three methods discussed above, only the capillary rise method can be used to measure the absolute value of surface tension. The other two methods require a second liquid for comparison. Next is surface tension and chemical constitutions. McLeod in 1923 found the following relationship between surface tension and density. Gamma raised to power 1 by 4 by D, capital D minus small d is equal to C, where gamma is the surface tension of the liquid, capital D is the density of the liquid, small d is the density of vapor at the same temperature, and C is a constant independent of temperature. Equation is found to hold good over a wide range of temperatures for normal liquids. Sugden in 1924 made use of above equation to relate surface tension with the chemical constitution of the liquid as follows. On multiplying both sides of equation with the molecular masses of the liquid, we get m gamma raised to power 1 by 4 by capital D minus small d is equal to mc and is equal to a constant p, and thus obtained is called parature. Hence, a parature of a liquid is the molar volume of the liquid at a temperature at which the surface tension of the liquid is unity. The application of parature is deciding chemical constitution of a liquid is based upon the fact that the parature is an additive as well as constitutive property. The additive property of a molecule is defined as that property, the total value of which is the sum of the value of its constituent atoms. Thus, each atom has a definite value of parature, and the total parature value of the simple molecule is the sum of the parature value of the constituent atom. The parature value associated with the atoms are called atomic paratures. A constitutive property of a molecule is defined as that property which depends upon the constitution of the molecule, that is, arrangement of atoms within the molecule. In case of parature, it is found that the total parature values of a molecule containing some multiple bond or a closed ring, etc., depend not only upon the atomic parature but also upon the multiple bond or rings present. The parature value associated with the structure of the molecule, that is, the multiple bond closed rings, are called structural paratures. The parature is an additive property and is supported by the following two facts. First is isomeric compounds have nearly the same parature values. Second is the difference between the paratures of successive members of a homologous series is nearly the same in different homologous series. Next is the similar studies have been made for the other homologous series such as alcohol, ester, aldehyde, ketone, etc. Next is the parature is a constitutive properties and which can be supported by the following example like for the ethylene. In case of compounds containing a double bond or triple bond or a closed 3-membered or 4-membered or 5-membered ring, so the observed value of parature is found to be higher than sum of the atomic parature. So this shows that these structures make a definite contribution towards the total parature of the molecule. The application of parature is the deciding chemical constitution of a liquid may be illustrated with the help of following example like the structure of quinone and structure of benzene, structure of para-aldehyde, and the experimental values of parature of all these are experimentally calculated, which is close to that of the calculated for those structure. It is of interest to mention that for any liquid using the calculated value of parature and experimental value of density and knowing the molecular mass of the liquid, the value of surface tension can be easily calculated. Next is viscosity. It is well known that all liquids do not flow with the same speed. Some liquids like water, ether, etc. flow rapidly, while some other liquids like glycerin, castor oil, etc. flow quite slowly. This indicates that every liquid has some internal resistance to flow. The internal resistance to flow possessed by a liquid is called its viscosity. The liquids which flow slowly obviously have high internal resistance and therefore are said to be more viscous or are said to have high viscosity. On the other hand, the liquid which flow rapidly have low internal resistance and hence are said to be less viscous or are said to have low viscosity. To understand the nature of the internal resistance or friction existing within the liquid, consider a liquid flowing through a narrow tube. All parts of liquid do not move through the tube with the same viscosity. velocity, imagine the liquid to be made up of large number of thin cylindrical coaxial layers. The layer which is in contact with the walls of the tube is almost stationary. As we move from the walls towards the center of the tube, the viscosity of the cylindrical layers keep on increasing till its maximum at the center. Conversely, we may say that as we move from the center towards the wall, the velocity of the layers keep on decreasing. In other words, every layer offers some resistance or friction to the layer immediately below it. This force of friction which one layer of the liquid offers to another layer of liquid moving with the different velocity is called viscosity. It has been found that the force of friction between two cylindrical layers, each having area A square centimeter, separated by a distance x centimeter and having a velocity difference of v centimeter, is given by F is equal to F is directly proportional to A into V by X, where N is a constant known as coefficient of viscosity. Hence, coefficient of viscosity may be defined as the force of friction required to maintain a velocity difference of 1 centimeter per second between two parallel layers 1 centimeter apart and each having an area of 1 square centimeter. Some important result. Fluidity. The reciprocal of the coefficient of viscosity is called fluidity and it is usually represented by phi. Fluidity is in fact a measurement of the ease with which a liquid can flow. Second, flow through a capillary. It was given by Poiseuille that the flow of liquid through a capillary tube is governed by the following expression. So here it is equal to pi p into r the power 4 t by 8 VL, where V is the volume of the liquid that flows in time t under a constant pressure P through a capillary tube of length L and radius R, and N is the coefficient of viscosity. Unit of viscosity and fluid. So, as discussed above, the unit of viscosity is Dan centimeter per Dans second per centimeter square. The viscosity of a liquid decreases with the increase in temperature. It has been found that the decrease is about 2% per degree rise of temperature. A number of equations has been proposed connecting viscosity and temperature. The best out of these is one given by Arrhenius for pure liquid, where the above equation is written as log of N is equal to log A plus E by RT. Next is measurement of viscosity. The absolute value of the coefficient of viscosity can be determined by measuring the various parameters involved in the Poiseuille's formula. However, for most of the purposes, it is sufficient to find out the relative viscosity, that is, viscosity with respect to water as reference. This eliminates the necessity of the measurement of number of parameters of the above formula as explained below. For a liquid flowing under its own hydrostatic pressure, P is equal to HdG, where H is the height of the liquid column, D is the density of the liquid, and G is the acceleration due to gravity. For equal volumes of two liquids flowing from the same height through the same capillary that the length L and the radius R are same, if N1 and N2 are the coefficient of viscosity of the two liquids, D1 and D2 are their densities, and T1 and T2 are the respective times of flow. Then N1 by N2 is equal to D1 T1 by D2 T2. Thus, the measuring the times of flow of two liquids, knowing their densities and knowing the coefficient of viscosity of one of the liquids, that of the other can be calculated. The apparatus used for the measurement of relative viscosity based upon the above formula is called a viscometer. The simplest is the one given by Oswald and is called Oswald's viscometer. It is shown diagrammatically It consists essentially of a bulb B to which is sealed a tube above and a capillary below. There is mark M on the tube and mark M dash on the capillary as shown. The lower end of the capillary is sealed to the bigger bulb C and a wider tube DE. The complete apparatus is U-shaped. The procedure consists of the following steps. The apparatus is first washed with the chromic acid and then thoroughly with water. It is then clamped vertically and a rubber tube is attached to the end A. A definite volume of water is introduced in the bulb C through the end A. The quantity of water added should be more than the required to fill the bulb B. Through the rubber tube attached to the end A, distilled water is sucked up into the bulb B so that the level of water is a little above the mark M. The water is then allowed to flow back and the time taken for the water to flow from the mark M to M dash is noted. The apparatus is then dried and the experiment is repeated as above, taken the same volume of the experimental liquid. The result is then calculated using the formula derived above. So next is viscosity and the chemical constitution. No significant relationship between viscosity and chemical constitution has been put forth so far. However, some general results have been observed which are summarized below. First, in a homologous series, the viscosity increases as we go up in a series and the increase per CH2 group is almost constant. In compounds involving chain isomerism, the N isomers have generally greater viscosity than the branch chain isomers. In compounds involving geometrical isomerism, trans isomers have generally higher value of viscosity than the corresponding cis isomers. To predict whether a liquid is associated or not, Dunstan proposed a rule called Dunstan's rule. According to this rule, for normal liquid, that is non-associated liquids, the value is much higher than 80. The value of a few associated and non-associated liquids are given. Like for benzene, it is 73. Toluene, it is 56, which are non-associated. For the associated liquids like water, it is 559. Glycol, it is 2750. Next are rheochore. Just as parature is an additive and constitutive property related with surface tension, efforts were made to derive a similar quantity related with viscosity, which should be additive and constitutive in nature. One such quantity found has been named as rheochore, which is related to the viscosity by the following expression. R is equal to m by d into coefficient of viscosity raised to power 1 by 8. Hence, rheochore may be defined as the molar volume of the liquid at a temperature at which its coefficient of viscosity is unity. However, the use of rheochore is as an additive and constitutive property was found to be very limited, hence the term could not gain any significance. It may be mentioned here that the most important application of the measurement of viscosity is in the determination of molecular masses of polymer by finding the viscosities of their solution in appropriate solvent. The principle of such a determination is as follows. If the viscosity of the solution is N at concentration C and the viscosity of pure solvent is N naught, then the specific viscosity of a solution is defined by the relationship N minus N naught by N naught is equal to NSP. So, the plot of NSP by C versus C is found to be linear, and the value obtained by the extrapolating the plot to zero concentration gives what is called intersonic velocity. It is found to be related to the average molecular mass of the polymer. Next is refractive index. When a ray of light travels from one medium to another, it undergoes a change in direction as shown. This phenomenon is called refraction. If the ray of light travels from a less dense medium to a more dense medium, the ray is bent towards the normal. It was observed by Snell that if a ray of light travels from air or vacuum to a more dense medium, then the ratio of the sine of angle of incidence to the sine of angle of reflection is constant depending upon the nature of the medium, and this constant is called the refractive index of the medium and is usually represented by mu, that is sine I by sine r, and this is called Snell's law. The value of refractive index is also found to depend upon the wavelength of the light used and the temperature. These are usually specified as subscripts and superscripts respectively, and thus mu d 20 degree indicates a refractive index taken at 20 degrees Celsius with light corresponding to yellow D line of the sodium spectrum obtained from sodium vapor lamp. Alternatively, the refractive index of medium is also defined as the ratio of velocity of light in vacuum to the velocity of light in the medium. In the Snell's law defined above, the first medium chosen is air or vacuum. In general, if a ray of light travels from any less dense medium to any more dense medium, it has been observed that sine I by sine r is equal to capital N by small n, where small n is the refractive index of less dense medium and capital N is that of more dense medium. Next is measurement of refractive index. The arrangement of refractive index is based upon the phenomena of total internal reflection and critical angle. Let us therefore first try to understand these phenomena clearly. Suppose a small source of light is placed in a line with the interface of two media. R1 to R6 are called incident rays, and as the angle of incidence increases, angle of refraction also increases. The ray R3 is almost going along the interface. The angle of incidence for the ray is therefore nearly 90 degree. This angle is called grazing angle of incidence. Thus, for the rays R1 to R3, for which the angle of incidence is less than 90 degree, the refracted rays are R1 dash to R3 dash. The rays like R4, R5, R6, etc., having angle of incidence greater than 90 degree, undergo reflection with the medium second, and the corresponding reflected rays are R4 dash, R5 dash, R6 dash. This is called total internal reflection. For the ray R3, angle of incidence is nearly 90 degree. The corresponding angle of refraction is the maximum angle of refraction and is called critical angle, usually represented by E. It may be seen that a bright band of light will observed corresponding to the refracted rays R1 dash to R3 dash with darkness on either side. The edge of the bright band corresponding to R3 dash will give a measure of the critical angle, and the edge of the bright band can be observed by placing a telescope which can be rotated about the point O. The instrument used for the measurement of refractive index is called refractometer, and the two most common refractometers are Pulfrich refractometer and Abs refractometer. The first refractometer is used for precise measurement, where the second is used for rapid measurement. The second, that is Abs refractometer, is briefly described below. The principle for the Abs refractometer is represented in figure 2.30, whereas the design of the instrument is shown in figure 2.30b. It consists essentially of two right-angle prisms P and Q with their hypotenuse faces together. These can be clamped together with a clamp X in a metal box hanged at Y as shown in figure. The box is attached to an arm R with the help of which the prism system can be rotated and the value of refractive index can be read directly on the circular scale fixed at the top of the arm R. The hypotenuse face of the lower prism P is crowned, whereas that of upper prism Q is polished. A drop of liquid is placed on the hypotenuse face of prism P, which spreads between the two faces when the two prisms are fixed together. The light from a suitable source is then reflected by the mirror M onto the liquid layer, as shown in figure 2.30a. On striking the ground surface of the prism P, the light gets diffused in all directions. Thus, the rays are incident to the polished face of the prism Q at angles less than 90 degree and at angles greater than 90 degree. A picture of this concept is shown in figure 2.30. The rays incident at angle greater than 90 degree undergo total internal reflection within the prism Q and do not come out of the prism Q. The rays incident at an angle less than 90 degree undergo refraction and come out of the prism Q in the form of a bright band of light. To observe the edge of the bright band corresponding to the grazing incidence, a telescope is fixed above the prism system and the box containing the prism system is rotated till the edge of the bright band coincides with the cross wire of the telescope. This setting corresponds to the refracted ray refracted at the critical angle E. However, instead of measuring the angles, the circular scale is graduated directly for reading the refractive indices. A few important points about the abyss refractometer can be mentioned as follows. For the critical angle phenomena to occur, the refractive index of the liquid must be less than that of the material of the glass prism Q. If white light is used, as is usually the case, a diffuse color edge is observed in the telescope. To make the edge sharp and to remove the color, compensating prisms are fixed behind the objective of the telescope. As the refractive index depends upon temperature, therefore to keep the temperature constant, a prism box is enclosed in a water jacket. An important advantage of the instrument is that it requires only a few drops of the liquid. Next is refractive index and the chemical constitution. Attempts have been made to relate the chemical constitution of a substance with its refractive index. Thus, a number of new terms have been put forward as explained below. Specific refractivity. It has been found that for any substance having refractive index N and density D at same temperature, the expression R is equal to n square minus 1 by n square plus 2 into 1 by D is constant for the particular substance and is independent of temperature. The quantity R is called the specific refractivity or specific refraction of the substance, and this term was put forward by Lorentz in 1880. Next is molar refractivity. Multiplying the specific refractivity by the molecular masses of the substance, we get what is known as molecular refractivity or molar refraction R. And the above formula is applicable to gases, liquid as well as to solid. And to determine the molecular refractivity of a solid, it is dissolved in a suitable solvent and the refractive index N and density D of the solutions are measured. The molar refractivity Rs of the solution is then given by formula n square minus n by n square plus 2 into x1 m1 plus x2 m2 by D, where x1 and x2 are the mole fractions of the solvent and solute respectively, and m1 and m2 are their molecular masses. But the total molar refractivity of the solution is the sum of the contributions made by the solute and the solvent. Hence, Rs is equal to x1 R1 plus x2 R2, where R1 is the molar refractivity of the solvent and R2 is that of solid. Thus, knowing R1, R2 can be calculated. Like Parcher, molar refractivity have been found to be additive as well as constitutive, and the additive nature is supported again by the fact that the difference in the molar refractivity of the successive number of a homologous series is nearly constant, and the isomeric compounds with similar structures are found to have nearly same values of molar refractivity. Similarly, the constituent nature is supported by the fact that in case of compound containing double bond, triple bond or a closed ring, etc., the observed value of molar refractivity is higher than the values obtained by simply adding the atomic refractivities. The values of atomic refractivities have been calculated in a manner similar to that done for parature. Tables are available for consulting these values. However, while calculating the molar refractivity, the following 2 points must be kept in mind. The atomic refractivity of oxygen atom is different in alcohol, ethers and ketone, and when a compound contains more than one double or triple bond, the molar refractivity depends not only on the number of double or triple bond but also on their relative position in the molecule. When the double or triple bonds are present in conjugated position, the molar refractivity is higher than the calculated value, and this is called optical exhalation. The application of molar refractivity in deciding chemical constitution of a substance may be illustrated with the help of some example. However, even this method has found only limited application in deciding chemical constitution. Thank you all.